Welcome to video on radio frequency integrated circuits, that is RF ICs, which is a part of our LMRF course. So objective of this particular course is what are RF ICs, why RF ICs are required, and what are the specifications of RF ICs. So what are these RF ICs? So ICs that operate at RF frequencies are called as RF ICs. So naturally the ICs which operate at radio frequency are uh, as the frequency increases, the circuit components behavior changes. So assume that we have already studied so many ICs like ADC IC, DACs, and we have studied op amp, triple five timer, all those things. So those are again the ICs which operate at very low frequencies in terms of hundreds of kilohertz and megahertz. As the frequency further increases, the circuit component which is used to realize those ICs will behavior totally differently. So their behavior changes. We have to be more careful while designing the ICs which are operating at radio frequency. So with more parameter analysis. So we need to consider so many other parameters while designing these RF ICs which are operating at very high frequencies in terms of megahertz. So why RF ICs? So as a circuit designed for low frequencies will change its characteristics, more stringent design specifications are there for RF ICs, and we need to have a more specific IC packaging that is required to avoid the radiation effects, because we are operating at very high frequencies. The circuit starts radiating the signal, and the circuit operation will be affected by the external radiations. So we need to have a specific IC packaging, especially for this radio frequency ICs. So what are the RFIC specifications? So we know that low frequency ICs, usually the specifications are in terms of the gain, the 3 dB bandwidth, unity gain bandwidth, power dissipation, and of course we can also have few more parameters like input impedance, output impedance, like input impedance very high, output impedance very low. So whereas for RFICs, so we certainly have these 3 to 4 specifications which are there for low frequency, like gain, 3 dB bandwidth, unity bandwidth, and these are some of the new parameters or specifications that will be specific for this RFICs, like VSWR, which stands for voltage standing wave ratio. So this is actually voltage standing wave ratio, and there is a IIP3. So we shall find out what is this IIP3, and 3D compression point, and input and output impedances. So these are the main specifications. Along with, we want to also have what is a power rating of the ICs, and what is the noise factor, what is the SNR of all these ICs. So these are the major RF IC specifications. Now, what are the important terminologies of RF circuits? So most importantly, we'll talk about the impedance matching, reflections, and VSWR. So these are very important terminologies when we are discussing any RF circuits. So what is the impedance matching? Whether the impedance of the input and output is it matched? Is there any reflections? Is that reflections resulting in any standing waves on the ports? So these are the very important parameters which will be considered while discussing the RFICs. And we also talk about the return loss. So once we apply some signal, whether the entire signal is delivered to the circuit or is anything that is returning. So that's what we call it as return loss. And we have this linearity. So linearity, as the name itself indicates, supposing that we have an amplifier application realized using RF circuits. So whether the amplification is constant throughout all the input amplitude, or does the amplitude is actually changing the gain of the system. So that's what we call it as linearity. And harmonic distortions, whether the output is coming at a desired frequency or some other frequency is also coming. And over next is the dynamic range. So this is the range over which the output is satisfactory with that desired specifications. Noise factor is again the signal to noise ratio of the output and the input of that RFICs. And we have an important discussion on 1 dB compression. which will again talk about the linearity of the usually the amplifiers, and we have this IIP3. So we will discuss this, what is this IIP3. Next we also have this OIP3, and we have a directivity discussion, and we have the isolation. So isolation is, okay, if you have more than one input, so how does the one input is isolated from the other input, because there should not be any crosstalk between the inputs itself. So we need to have a good isolation between the two inputs as well as the output. And types of RF ICs are, they can be amplifiers, mixers, modulators, splitters, and impedance matching ICs. So these are the few important RF ICs that we'll be discussing in this particular course: amplifiers, mixers, modulators, splitters, and the impedance matching ICs. So this is what is impedance matching. So we have a RF circuit, and we have a source connected here, and we have a load. So we know that whenever we connect a source, so that source will going to give the voltage to this RF circuit. Suppose if the impedance of the source and the load are not matched, so we're going to end up with the reflections. Now this is the incident ray which is going into the RF circuit, and there is some signal which is reflected back from the input because the impedance is not perfectly matched with the source impedance. So that's why it is coming back. So incident ray and reflected ray. Same thing will happen for at the load. If the load impedance is not matched with the output impedance of the RF circuit, we have the incident signal which is going to the load, and load is actually reflecting some signal. This is the reflected signal at the output node. This is what we are talking about impedance matching. So there is a RF circuit, will have some input impedance. This is the source having the input voltage, and ZS is the source impedance, and RF circuit has got some output impedance Z out, and this is the load impedance. If Zin is equal to Zs, then the entire voltage will going to reach over here, so there will be no reflections. If this Zs and Zin are not equal, then we'll end up with some reflections, so that will reflect back to the input. So same thing happens over here. So this load has to actually take all signal. Suppose the impedances are not matched, so it will not accept everything, it will reflect something back. So we're going to have a reflections at the output port as well as at the input port. So as we discussed, this return loss is, okay, how much amount of signal is going back to the load, going back to the circuit, or going back to the source. Now in this case, return loss of the port 1, how much you are returning back to the source. So in case of this output node, how much power is returned back to the circuit. So this is what is return loss at the output node and the input node. So let us try to find out, okay, how do we find out this VSWR, the standing wave ratio. So we know that there is a source, and there is a source Vs having an input impedance of Zs. There is an RF circuit having some input impedance, and it has got some output impedance also. It's connected to a load of ZL. So as soon as we connect this, so there is an incident signal going into the RF circuit. If the impedance is not matched, we're going to have some reflected signal going back to the source. Same thing happens here. The output will be delivered to the load. This is your incident signal to the load, and load will reflect something, some signal if this load impedance is not equal to the output impedance of this. So the VSWR can be expressed in terms of the return loss, which is 1 plus 10 power minus RL by 20, and 1 minus 10 to the power minus RL by 20. This RL is the return loss. We can also express the reflection coefficient, which is the ratio of reflected to the incident voltage. So this rho, which is the ratio of reflected voltage to the incident voltage, which can be related to VSWR using this equation. Now let us see, okay, how does a VSWR pattern looks like. So assume that this is the incident and reflected waves on a transmission line terminated with open circuit. So open circuit means, okay, it is not connected to any load. Since open circuit is also a load, so what will happen is, so you can see now there is a incident signal I, which is being represented as a solid line, and this is a dotted line, which is the reflected signal. So this is the load point here. So the incident signal is going here, and there is a reflected signal which is being totally reflected because the output is open circuit, so nothing is delivered there, so everything is get reflected back here. Now if you can carefully observe, at this point both are having same magnitude as well as same phase, so that's why the VSWR is the pattern of the VSWR is maximum here. So if you can clearly observe at this dotted line, so we have a magnitude corresponding to incident and the magnitude corresponding to the reflected here. uh, they are almost same in magnitude, but the phases are exactly opposite. When the phases are opposite and the magnitude is same, we end up with a zero difference there. So the difference of the incident and the reflected becomes zero here. Now you can see VSWR changes from maximum to minimum and again goes to maximum. You can see why it is again maximum here is, even though the magnitudes are same, the phases are also same. So it is the vector addition of the incident, the reflected signal is standing wave pattern. So this is a standing wave pattern where you are vectorially adding the incident as well as the reflected signal. When they are in same phase, same magnitude, they add up to the maximum. Now they are of same magnitude but out of phase, so it becomes zero. At intermediate point, their magnitudes are different as well as their phases are different. So I can see it is keep on increasing, then it is keep on reducing. So we're going to have some minimum VSWR value and there is some maximum VSWR values. So this how a standing wave pattern will be get generated because of the incident in the reflected waves. So in the next few pictures, we shall see different types of VSWR patterns. So this is a VSWR pattern for a perfectly matched load, so where we don't have any reflected signal. So it will end up with a straight line, that is the VSWR pattern will be a straight one. Suppose there is a slight mismatch. Now you can see the VSWR minimum is not totally becoming zero. So the cancellation is there, but it is not totally zero. So we end up with this type of pattern for a VSWR, which is not fully reflecting. So when it is fully reflecting here, you can see when it is totally reflecting, the V minimum is zero. So this will end up with a VSWR which is maximum here. Now here it is the minimum possible value of VSWR, which is 1. VSWR maximum depends on what is the height of this magnitude and this magnitude. And you can see these are the two intermediate VSWR patterns where it is neither the minimum nor the maximum. Now you can see we can have different VSWR patterns depending on the terminations. Now you can see if the termination is an inductive one, we're going to have first minimum comes and then the maximum comes. Here if the termination is capacitive, you can see now first you have this is not fully minimum. So if it is inductive in nature, we'll get the first maximum. If it is capacitive, we'll get the first minimum. If it is resistive, we're going to have either maximum or minimum depending on whether the resistance is maximum or minimum. So if the resistance is if the load is purely resistive, we'll end up with either maximum VSWR position or the minimum VSWR position. Suppose if it is capacitive, we will end up with some intermediate value. The next immediate value will be the minimum. If the load is inductive, we'll end up with some intermediate value. The next immediate value will be the maximum. So we'll first end up with maximum if the load is inductive. We first end up with a minimum if it is a capacitive in nature, if the loads are capacitive in nature. So this is what we call it as linearity. We know that for all input power, we expect the output voltage to be keep on increasing. But actually what happens there is, up to certain voltage, the output voltage follows the input voltage with that whatever gain specified. After some point, you can see the output voltage saturates. Now this is from here to here, we can call that the circuit is linearly behaving. So after that, the behavior is not linear, so it will be a saturated one. So this is what is linearity. For a good RF circuit, this should be linear for a larger input voltage level. And we have the next important discussion as 1 dB compression. We know that this is the ideal expected graph, whereas typically it goes like this. Wherever for whichever input voltage, input power, we have the output power less than 1 dB expectation is called as the 1 dB compression. So we'll discuss this in next video.